This video is on electric charging. I'm Mrs. Estock. Let's get started. Let's begin by reviewing the basic structure of an atom. Inside of an atom, we have the following particles. The electron is negatively charged and orbits the nucleus. And within the nucleus, we have the proton, which is positively charged, and the neutron, which is neutral. These are the three main particles of the atom. Two out of those three particles have electric charge, the proton and the electron. The protons have a positive charge, and the electrons have a negative charge. The charges of those two subatomic particles are responsible for the two different kinds of electric charge, positive and negative electric charge. When we say that an object is electrically charged, we are talking about the ratio of protons to electrons. If an object has more protons than electrons, it's positively charged. Or if it has more electrons than protons, it is negatively charged. Which brings us to the fundamental law of electrostatics. When charged objects interact with other objects, electric forces result that either attract or repel the objects. Like charges, such as positive and positive, or negative and negative, repel each other. In other words, they push apart from each other. Whereas opposite charges, positive and negative together, attract. We also learned in our activity that charged objects attract neutral objects due to a phenomenon called polarization. All objects charged and neutral follow these rules, from the very big to the very small. Back in modern physics, we learned about the four fundamental forces of the universe. There were electromagnetic forces like these, gravitational forces, and also strong and weak forces. We also learned that electromagnetic forces are much stronger than gravitational forces. We saw that also in our activity. Just a little PVC pipe charged up with some wool can overcome the entire pull of gravity downward on that little pith ball. So if electrical forces really are that much stronger than the force of gravity, why don't we usually feel electrical forces of attraction and repulsion in our everyday lives? We can certainly feel gravity holding us down in our chair, but we don't really feel repelled, right? Or do we? Well, it turns out that most objects are neutral. They have the same number of protons and electrons. And neutral objects will not apply electric forces to other neutral objects. So because most objects are neutral, we don't typically feel electrical forces like we feel gravitational forces. Also, electric charge is always conserved. We can transfer charge between objects, but that charge cannot just appear out of thin air or disappear forever. Electric charge just gets passed from one object to another. The two units of electrical charge are the coulomb, which is the SI unit of charge, and the elementary charge, which is the charge of an electron or a proton. So when you say that a proton has a charge of +1, what you're really saying is the proton has a charge of +1 elementary charge. One elementary charge is equal to a teeny tiny fraction of coulombs. So coulombs are a much bigger unit of charge than elementary charge. We use coulombs as the SI unit for charge in calculations because it's more useful for large quantities of charge. But if we're referring to electrons and protons, the charge on an electron is either -1 elementary charge or -1.6 times 10 to the -19 coulombs. Similarly, a proton has either a charge of +1 elementary charge or +1.6 times 10 to the -19 coulombs of charge. Here's how you might see this used in practice problems. An object has 10 protons and 16 electrons. What is its charge in both elementary charges and coulombs? To figure out the overall charge, think about the amount of charge from those protons and electrons and add them together. 10 protons would have a charge of +10 e, and 16 electrons would have a charge of -16 e. If we add those together, keeping the positive and negative signs with their associated charges, you get an overall charge of -6 elementary charges, which means that we have 6 more electrons than we do protons. So that number is giving us the ratio of electrons to protons. To figure out how many coulombs of charge, we take our value from part A, -6 elementary charges, and we convert that from elementary charge to coulombs by multiplying it by our conversion factor. 1.6 times 10 to the -19 coulombs goes on top because we're converting to coulombs, and that's equal to 1 elementary charge, which we put in the denominator because we want to cancel out elementary charges and end up with coulombs. Our final answer is -9.6 times 10 to the -19 coulombs of charge. A neutral object loses 5 electrons. What is its charge in elementary charges? So when you think of this question, I want you to think about the double negative here. When an object loses electrons, it's becoming less negative or more positive. So if a neutral object loses 5 electrons, it would have a resulting charge of +5 elementary charges because now it has 5 more protons than it does electrons. Suppose an object with a charge of -34 elementary charges gains 7 electrons. What is the new charge? So again, think about the electrons and what happens if you gain electrons. If the object is adding more electrons, it's becoming more negative. So that means if I take the original charge, -34e, and add 7 units of negative charge, becoming more negative, I would get -41 elementary charges as the new charge. Now that conversion has been sitting up there for a minute. Now we'll see what I actually wrote that for. That is for the third question. If we were to convert the answer from number 2 from elementary charges to coulombs, we would use the same process that we went over before. Multiply the value by 1.60 times 10 to the -19 coulombs per 1 elementary charge, giving us a charge of -6.56 times 10 to the -18 coulombs. So now that we know a little bit more about charge, and we know more about the units of charge, coulombs and elementary charge, we can start talking about transferring charge. So charge can be transferred from one object to another by moving electrons. There are 2 types of materials that we'll refer to in this unit, and the type where electric charges like electrons can move freely are called conductors. Typically, these are materials that are made out of something metallic like copper, aluminum, or silver. These are the types of materials that we'll be using in our labs and also the materials that conduct electricity, like the copper wiring in circuitry. So these types of materials allow electrons to move freely, so the electrons can easily jump from one atom to another. And notice in this little animation here, it's the electrons in the diagram that are moving, because remember, the electrons are the particles that are on the outside of the atom that are not bound to the nucleus. Those protons are stuck in place. They're bound in the nucleus. They're not going to move just because there's a positive pipe there. A stronger force, called the strong force, is keeping them contained within the nucleus. The opposite of a conductor is an insulator. Materials that do not allow electrons to move freely are called insulators. Examples of insulators include glass or rubber. It includes the coating on wiring, like the rubber coating on wires to keep those electrical currents flowing. And you can see in this example animation, the electrons aren't moving quite as much as they were in the other animation for conductors. So they can still shift a little bit, but they're not really jumping from one atom to another. That's because this material is an insulator. A way that we're going to measure electrical charge in our labs is a device called an electroscope. Electroscopes simply measure the presence of charge. They don't actually tell you if the charge is positive or negative, just that it's there. The type of electroscope that we'll be using in lab is called a gold leaf electroscope, very fancy. And the other type is called a needle nose electroscope, or a needle electroscope. You can tell that charge is present in an electroscope when the leaves or needles are deflected. In other words, they're pushing apart, because if both of the leaves are the same charge, like charges repel. So you can tell if both the leaves are positive or both the leaves are negative if they are repelling from each other. This is an experiment that we'll be doing together in class, using electroscopes to charge by different methods. The different methods of charging that we'll be using in class include the following. Charging by conduction is when you have direct contact. So if you physically touch a charged object to another object, you are charging by conduction. This is transferring electrons through direct physical contact. So if you charge up a PVC pipe to be negative, and then you touch that negative PVC pipe to, let's say, a pith ball or an electroscope, the electrons are going to move directly from the PVC pipe into the object. That is called charging by conduction. Another example is when you touch a doorknob and get an electric shock. That's because the doorknob is transferring charge between you and itself, moving electrons from one object to another. In this case, electrons are being transferred, so charge is still conserved. The electrons are leaving one object and moving into another object. They're not just being created out of nowhere. Here's an example animation of what it looks like to charge by conduction. Notice in the example there's direct contact. So if you move a positive object and touch, let's say, an electroscope, some of the electrons in that electroscope will move into the positively charged object, making the electroscope positive as well. So another important point about charging by conduction: the object involved in this charging process, in this case the electroscope, will receive a charge that is the same as the charged object being used. So in other words, in this case, a positive rod is making the electroscope positively charged. It's becoming positively charged because it's losing electrons. Another charging method that we'll use in class is charging by friction. Charging by friction is when you scrape two objects together. really scraping electrons off of one object and onto another. If you scuffle your feet on the ground, you're charging by friction. If you rub a PVC pipe with a piece of wool, you're charging by friction. And again, in each case, it's only the electrons that are moving. So you can transfer electrons from one object to another, but those protons are stuck in place. They're locked into the nucleus. They're not going anywhere. Another type of charging is charging by induction. So this one is a little trickier. It is a type of charging that requires no direct contact between the object and the charged object. So charge is not actually transferred from the charge rod itself. Rather, charges are shifted between the other two objects involved. So here's how charging by induction works. Let's say you have, like in the diagram in the lower left-hand corner, a charged rod. Let's say you charged a PVC pipe to be negatively charged, and you bring that charged object close to but not touching two conductive metal spheres that both start out neutral with equal numbers of protons and electrons. When that charged rod is brought close to but not touching the spheres, the electrons within the metal spheres are going to be repelled from that negatively charged rod. So some of those electrons are going to move away from the charged rod from one sphere into the other. This transfer of charge between the spheres results in one sphere, the one here on the right-hand side, being negatively charged because it gained electrons, and the metal sphere on the left-hand side has become positive because it lost electrons. While the charge rod is present, if you separate those two metal spheres, the result will be that one sphere is positively charged while the other is negatively charged. So you've essentially charged these two metal spheres without ever actually touching them. You're exerting these electric forces that are field forces without direct physical contact. So the charges are transferred between the spheres and not from the charged object itself. Here's what this looks like, step by step. Bring it close to but not touching. You could ground the electroscope in this case, drawing electrons into the electroscope, making it negative. So positively charged object used by charging by induction will draw electrons from ground to make the electroscope negative. So an important point here with charging by induction, when you're charging by induction with the electroscope will acquire the opposite charge as the charged object used. So in this case, a positively charged rod made the electroscope negative through induction. Last but not least, let's define polarization, because this is one of the key pieces of charging, especially charging by induction. Polarization occurs when the charges within an object align themselves in a way that is not evenly distributed through the object. So the alignment of charges changes, resulting in more positive charge on one side of the object than the other. This can happen with neutral and charged objects. And it's also the reason why if you stick a balloon to the wall, it will stay there. So you can see in the animation that the wall becomes polarized by the negatively charged balloon. So when you rub a balloon on your hair, the balloon becomes negative, your hair becomes positive, and probably sticking up in all directions. And when you stick that balloon to the wall, the negative charges in the wall are going to push away from the balloon, leaving the side of the wall next to the balloon positive, and that's how the balloon can attract to the wall.